Here, Chuck. It's wonderful, actually. Good
And
day.
I'm going to turn on Morten Simonsen as well. Morten, you're in Copenhagen.
That's correct. Hello to you. Happy
Welcome
to
to the
here.
webinar. So let's proceed and talk about what we're going to do. We're going to do a brief history of HD radio. It's fascinating. We have 340 people registered for this webinar, and many of them are from all over the globe. Many of them may not know much about HD radio. So we're going to provide a little history and the basics of HD radio. Not enough to bore the people that are already been running it for 10 years, but enough to get the basics. We're going to talk about something we call the RF Supercomputer, which is the brainchild of Morten Simonsen over there in Copenhagen. We're going to talk about a very interesting development and where we are today. We're going to focus in on PAPR and pre-correction techniques, and we're going to talk about where we as a company are going with regard to HD radio. And again, we will take your questions anytime during the webinar. So a brief history of HD radio. HD radio is the digital radio system which was developed for the United States, authorized by the FCC, and it offers multicasting and datacasting services, as well as allowing people to continue to broadcast in their existing analog broadcasts. It's a transitory technology, moving us from where we are today to the fully digital future, and it's in between where it allows you to have both analog and digital. It's been very successful. There are 2,300 US FM broadcasters offering HD radio, carrying 4,300 content channels. In the top 10 markets, 98% of the top 10 stations are using HD radio. HD radio is the digital standard in the United States, Mexico, Panama, and the Philippines. It's also on the air in Canada and in India. Here's the key one. Over 65 million HD radio receivers have been sold worldwide. You can't have a digital radio standard without the receiver side. We fought that for decades, but now we have 65 million HD receivers in the marketplace. And Broadcast Electronics, not to pat ourselves on the back too much, but we've been a leader in HD radio transmitters since the very beginning. So some basics, it's basically hundreds of digital carriers. It's OFDM added both above and below the FM analog signal. Combined power of the injection of the HD part or the digital part is somewhere between 10 dB below the analog or 20 dB below the analog, somewhere in between there. And it depends on the competitive environment, where you are, what stations are on either side of you, that sort of thing. And there are some good rules on that coming from the FCC. There are several methods of transmitting an HD radio signal, but today the most common is an exciter capable of simultaneously creating the analog and the digital components in the same exciter and following it with a PA running in Class A/B linear mode. And since any nonlinearities in the PA stage can cause spectral regrowth, adaptive pre-correction techniques are used to create or to correct those nonlinearities. How do we use this in the United States? If you're not in the US, you wouldn't know, but you can tune into a single radio station. For instance, this is WHUR 96.3, and you can hear the analog AM on an analog radio. But if you have a digital radio, it'll automatically switch you to the digital representation of the analog audio. In this case, it's 96.3-1. And on this radio station, I believe this is Howard University, they have the Steve Harvey Morning Show. But if you tune the dial one more click to the right, you'll go to 96.3, same frequency, but -2. And that's a world variety format, broadcasting culturally rich content to a diverse audience. And then 96.3-3 is R&B and a mix of new classic and soul. And 96.4 is a news talk station, all contained along with the analog on that same frequency, 96.3, on the same transmitter, on the same antenna. So this is the advantage of HD radio. This is something that has made it take off in the United States. And to top it off, you can add to that a bunch of data services such as Artist Experience, which is basically showing you the artist and title and maybe even a picture of the album art, iTunes tagging support, and very importantly, emergency alerting, which can use all of that, can use some of the available data bandwidth. And eventually, when most of the receivers in the field are HD radio compatible, that's not today, but in the future, the analog can be shut off, and that bandwidth can be available for more audio channels or services. This is how you do HD radio. These are the components. You may have heard some of these phrases and wondered what they are. An importer multiplexes the audio content channels into a single stream. The exporter creates the HD radio signal in what they call E to X form. So it's a particular protocol for transmitting from the exporter to the XGen. And then the XGen creates an INQ signal from the E to X data, which is fed directly to the direct-to-channel exciter. The exciter digitally synthesizes both the analog FM content as well as all the HD radio carriers and creates the total waveform on the RF frequency. It also receives a directional sample of the signal being fed to the antenna and compares it with the mathematically ideal signal, creating the error terms, which are then used to pre-correct the generated signal. It seems pretty simple. It turns out not to be so simple, but it works very well. And all of it in our implementation is all based on something we call the RF Supercomputer. This is a device which is made by a company called Pro Television in Copenhagen, Denmark. It's been designed primarily as a digital television modulator. And it is if you're familiar with SDRs, a software-defined receiver, this is an SDT. This is a software-defined transmitter. And you plug in the program, and it switches what kind of signal it creates. It can do all the digital television standards, even some analog television standards, as well as some radio. So it does DVB-T, DVB-TH, DVB-T2, ATSC, Legacy, or that's 1.0, or 3.0, ISDBT, or TBB, the Brazilian version, analog PAL and NTSC, DAB, TDMB, DAB+. This is why we call this thing an RF supercomputer. It operates from 30 megahertz to 760 megahertz in 1 hertz steps. And if you can think about a waveform, if you can think about a television or radio digital standard, this thing can create it. Imagine this PC card. It's 16 layers and over 2,200 parts. And it's a programmable RF supercomputer. It has an onboard web server with monitoring, no Flash or Java. It has 3 different levels of reference oscillator, which it means how long I can hold that exact frequency without having GPS. It does have GPS, but it also has GLONASS, Galileo, and BeiDou because this is an international product. It's got tons of technology. I could talk about this thing for hours, and I have, but I'd rather let my good friend Morten Simonsen talk about what he has accomplished in Copenhagen, Denmark. And Morten, I will give you the floor, and I will find a way to let you share your screen. So you're on, buddy.
Yeah, right now I don't need to share my screen actually.
Okay, I'll keep it on this slide then, if it's okay.
Yeah, that's fine.
All
So
right.
thank you for the nice introduction, Chuck. I think you could almost sell the RF supercomputer to me. Actually, you and me have done a webinar on this before, and that's why today I thought I will offer a little more action and show the thing physically. So when I've done a small introduction, I have both a dressed and an undressed card next to me, so I can show it on the camera.
Okay. Go
ahead. The RF supercomputer was born out of the fact that, especially when we started with HCSC1 and DVB-T, there came standards like the media flow from Qualcomm and the DVB-H and so on. And we realized that having to do new hardware each and every time was both too costly and had too much overhead, since it was to some extent like starting things all over again, and we would much prefer to accumulate our knowledge. And for that reason, in 2003, we actually used a couple of years on a systems level design where we said we need an open platform, at least open for ourselves, where we can develop and have the same environment for a long period of time. And that is what was the birth of the RF supercomputer. And actually, what we have today is the third generation hardware. So our hardware is luckily quite long-lived, and they are all compatible with one another. So even an owner of the first generation, of course there are a few exceptions, but in many cases, most cases, an owner of a first generation can replace that card, and the form factor, the electrical connections, the software protocol, and so on, mechanical is identical, and then such a customer can be good to go, for instance, with HCSC3. Now, these are exciting times for us. We have mainly our roots in television, and since we have been relatively recently acquired by the Elenos group, it is also my responsibility to streamline our radio products. And in connection with that, we have begun to implement also the radio waveforms on the RF supercomputer. The first one was the DAB, and I am happy to announce that this very week, we have actually for the first time also modulated iBook directly in the new HD radio firmware for the RF supercomputer. So that is a product that will become available pretty soon. We are still porting the FM part, and once that has been done, I think hopefully both you and Perry will be happy to see that we have such a very state-of-the-art product for our HD radio products.
Very exciting. Thank you.
Of course, we have been working with Xperi on this project. So what we call the X-Gene is the part that delivers our frequency domain symbols, but the rest of everything, interconnectivity, all the IP stuff I will talk about, and especially the precorrection and the signal processing and the very high signal integrity, of which I can proudly say that we are famous, is naturally all done by us. And as with any waveform for the RF supercomputer, to redefine it, as you said yourself, Chuck, it's almost like a software-defined transmitter. You simply load new firmware, and then you have the identity of a completely different product. And that can be done remotely or by a web server, a web GUI, where you just point to the firmware file, and then everything is automatic. And I think I will try to show the thing on top of all my bragging here. Do I control to put on the camera, Chuck? Chuck?
Let's find out. I don't know.
I will try to give it a go.
Okay,
Share my
let's see.
webcam.
Okay.
Do you see me as live sitting at the computer?
I don't. So I'm going to switch and make you the. I'm going to make you the presenter, and that should allow us to see you. Okay, now share your camera.
Show my screen, I presume.
Or your
I
camera.
can see Chuck.
Okay, we got you. We got you.
Okay. Hi guys. I am not so used to this kind of teleprompting news thing, so let's see how it goes. Nice to see you, everyone. So I will get a little closer.
We're seeing your user interface right now, the browser.
Yes.
Okay.
You see it in here behind, but I will try to go to the cam to show you the RF supercomputer. So this is a board.
We see you on the screen as well.
Yeah, you see the RF supercomputer close to the camera here, right?
We see, yes,
Yes. So I'm holding it in my hands. I hope you see it more or less taking up all the space.
Yeah.
Yes, I'll take 10 of them.
Yeah, thank you, Barry. That's a good beginning. This is how it looks like. As I said, this is the third generation. And just for your information, I think we are probably today above a total of 40,000 installed of base of these around the world. So the board, exactly as you said, Chuck, is a 16-layer board. We have 4 gigabit Ethernet ports here. These ports, they all have individual MAC address because some operators, they consider to have redundancy feed over IP. The endpoint really need to be an individual MAC address. We have the RF output, and then we have 2 sense inputs for feedback, respectively after the amplifier, and the output channel filter for the precorrection. I will come back to that. Then there is actually a connector here with a lot of programmable pins, so we can control and monitor many things. There's for the GPS antenna and some ASI and SIM310. There's expansion slot here for our internal processing machine, so that we can add future things. And I promise you there will be exciting things coming out from here. The opening you see here is the place where we can mount different qualities of reference oscillators, especially in single frequency networks. Especially some countries are teased by other countries. For instance, the military interrupt the service of the GPS system, which is used as a time reference. When that happens, the transmitter, and that in this case means the exciter, has to switch to a holdover mode so that it continues operating in the right phase and frequency. And the time that a transmitter can operate without external reference and without drifting away so much that it spoils the SFN is determined by the quality of the oscillator. And regretfully, the better the quality, the more costly the device. So for that reason, when we mount nothing like this, we are compliant with the standards of the phase noise. Then we can mount an oscillator of a step higher quality, and the highest quality is one with an oven that will run 24 hours SFN without interrupting the service. And of course, these oscillators, the calibration of them goes together with the device so that it can be plugged in the field without any skills other to put in the screws, and then it will automatically calibrate. Here we have a space, here we have a space for the optional GPS module. So this is what it looks like. The manufacturing is all by calibration by computers. There's not any manual work because when we do these quantities, we need to be a little bit of industrialized. And now let me show you a secret. Here comes the undressed RF supercomputer. So there's maybe something here for the little more technical. We see very, very powerful FPGA, Linux processor, memories, all the RF stuff, mixers and stuff. It was just to show you. You see the layout is pretty mature and neat. Now, precorrection is a thing that many speak of like it was the very highest technology, and it is. The thing is that theoretically, the theoretical, should I say, framework was created already in the late 19th centuries by an Italian called Vito Volterra. And he made a framework whereby any generic nonlinearity, including memory effects, can be linearized. So that means that is what we call a non-parametric model, because it just takes any nonlinearity and linearizes it. And this is exactly what we want. The mathematics are a little cumbersome, and regretfully, it doesn't lend itself well to calculation on anything less than a dedicated supercomputer. Nevertheless, the framework is so interesting that lots of research has been done to have an implication which you can actually execute on an existing computer. I will give you a small idea, and kindly let me know if you can see what I have written on the whiteboard. Is this readable?
We got to squint a little bit, but we can see you.
Maybe my kind assistants can help me a little. Is it better like this?
Much better, thank you.
Much better, thank you. I will just briefly show you. So basically, the Volterra system consists of kernels of coefficients, output signal, input signal, and these kernels, they are polynomial. It's like a Taylor series expansion. And a series expansion is a way of expressing some function, but by means of an alternative mathematical representation. What I am showing here is what we call, you see there are many dimensions. X you can regard as the time. Here there's a delay dimension. Here there's actually two delay dimensions. And here there's a delay and an advance. So the signal is convolved with itself in very many, in principle, indefinitely many positions in time. And this is what captures the memory effect of the signal. So I will make it short. So this is not a complete Volterra kernel. This is something that we can practically do in our machine. We save a lot of the complexity by taking the majority of the nonlinearity in a lookup table. Then we follow the lookup table with the Volterra kernel. And the Volterra kernel, we have made what we call a truncated kernel. So we don't run indefinitely long in all dimensions, but we have a subset of that. The wonderful thing is that this framework is so well functioning that I have not had to rewrite the precorrection ever when we meet a new waveform. It always works. It always works with any transmitter, DAO T, class A, B, or whatever. So that investment in a lot of mathematical efforts in the beginning has paid off really well. And I do believe we are still considered absolutely state-of-art company in this. So this was just, we are not going to talk so much about that. I would just like to show you kind of the concept behind it. So this kind of precorrector we do in any waveform. Thus, it is also what we will do when the HD radio is transmitted together with an FM signal. The paradigm changes a little bit when the digital is added to the FM, because the FM you can often do in a class F transmitter, because you can drive it almost to saturation and then filter away the harmonics. But as soon as you have CUFDM signals, then you have a requirement of linearity. Then you have to switch your amplifier to behavior operational mode, which is more linear. And that costs certainly efficiency. And then this is where mathematical schemes like these set in and can still save us energy and cost by extracting a linearity out of a transmitter, which is actually not very linear. If we get the time, you tell me how much talking time I have. I can show a demo of it running on a live transmitter here.
Please do.
Yeah, but I would like maybe to just wipe that and touch a little bit upon also the crest factor. So I will just, or the PAPR. Ja, lad nu være med at I will show you how, like this, how it works with the PAPR and also the nonlinearity. So why does a transmitter have a memory effect? That's an interesting question. Many papers has been written about that. Normally I use quite a basic way, which is the first order effect, to explain it. So I will just try to give you an idea. Is this readable?
Not so much yet. You want to
Not
zoom
so
in?
much. Maybe you would be kind to help again. Is it better here?
Better. Use a
Good.
dark marker.
I will try, yes. If we try to draw a baseband CUFDM signal, it is bandwidth limited noise, so I don't know how much better to draw in than something like that. The fact that such a signal has maybe an RMS around here, and the peak can easily be, let's say, plus 12 dB. So that means for efficiency reasons, if we need to be linear with such a large peak, we have to have a very large back off up to our power supply. In this case, 12 dB. So that costs a lot of power because we could do this power, but we generally only do this. Therefore, we want to reduce the peaks. When we do that, we bring the RMS closer to our performance of the amplifier determined by the power supply. And now I think I will just draw it the other way around. Say we want to reduce our crest factor, let's say to around 6 dB. But that means we cannot reproduce the peak. And when we, that means the amplifier only has capability to reproduce the signal like this, then it hits the saturation in this area. And instead of following with fidelity the waveform, which is bandwidth limited, bandwidth limitation will mean that there is a limit to the rate of change of the signal. But when we hit a hard limit, like the power supply being struck, we see that actually creates discontinuities. And so if we were to look to the equivalent of that in the frequency domain, we take the Fourier transform. And then let's say we have a CUFDM spectrum without any peaks. And then when we create discontinuities, you all know the signal begins to assemble more and more a square wave, and the Fourier expansion of a square wave has a lot of odd order harmonics. This is probably trivial to most of you, but we see it directly in the frequency domain as well. Now, Parseval's theorem tells us that there is a relationship between the energy distortion in the time domain and the energy distortion in the frequency domain. So that means we cannot just clip away and distort the signal by not reproducing this without paying a high penalty that is visible in both time and frequency domain. The interesting thing, however, and this is even before we talk maybe more waveform specific techniques. So given by Parseval, the area here, area 1, is physically related to the area here. So there is nothing we can do about that. That's a physical relationship. So the total area, the energy is the same. But we have one mechanism where we can actually shape, distribute the same amount of energy, but we can give it another distribution with frequency. And that means that the distance to the noise floor increases. And the distance to the noise floor is what we in the digital modulations call the MER. The analog people would call it carrier to noise, kind of similar. So simply reducing and using this noise distribution technique, we can actually improve the MER of the signal. And the ironic thing is, when the signal at the output of the transmitter, when it hits the channel filter, which cuts away the neighboring channels, that means we actually cut away part of this energy. And that means that energy is no longer there to suppress the peaks. So at the output of the channel filter, we regain some of the peaks. So that's a very interesting technique. I hope you like it.
That's very interesting. We've got about 3 or 4 minutes left for your part of this.
Okay. Then I will probably not even show the live demo, because I think now I'm getting all carried away. I hope you find it a little bit interesting. I will just show you what I was mentioning about the nonlinearity or the memory effect of the transistor. We have noticed that for a transistor to enter into saturation, so coming from a linear region and entering into saturation, requires less energy than taking a transistor out of saturation. So that means there's the transistor remembers if it has been coming from a linear region and going into saturation, or if it has been in saturation and going into the linear region. That's the strongest mechanism behind the memory effect. And simply just to illustrate that, that means that we cannot treat the signal when we do precorrection as if there was no memory effect, because then we would not be able to linearize in this very important region. And I think the concept of the memory effect is often, when I have been speaking with our customers, a little hard to comprehend, but normally many transmitter people know transistor devices so well that they, with this explanation, they recognize, yeah, that's a first order effect that I actually am aware of. So for that very reason, as the first order effect, it is literally necessary for us also to consider the memory effect when we do precorrection.
But interestingly enough, the people that are making HD radio transmitters in general haven't utilized memory effect precorrection. So this is going to be something new.
Yeah, I totally agree, Chuck. I am so keen now that we have it on our platform to see what it will bring to the market, because I have a strong expectation that we are head and shoulders above what has been seen, and hopefully that will bring a lot of value to our customers.
Of course, with better precorrection, it manifests itself either as improved MER, which could mean a better lock or a larger coverage area, or more efficiency. You
exactly.
Can turn it off.
You use it the way you like it, yes.
And Morten, this is appropriate to both television and radio, yes?
All waveforms which are multi-carrier, Perry, you are right.
Right.
So for the single carrier, we don't need it, because that's constant magnitude and only phase modulated.
Mm-hmm.
So that's an interesting times ahead of us to take, should I say, that technology that we have literally invested a lot of time and now we money, and now we have a lot of time-wise experience in it also gathered over the years, to be able to bring that to a new market. I think it will be interesting.
Morten, every time I hear you, I learn something new, and I'm sure that our listeners have learned something new from you, and I thank you for that. We've got lots more webinars planned, and you're going to have to carry that message a lot more detail going forward.
I appreciate it very much. Is it my task to try to shut myself down here, you think?
No, I can do it. No problem.
You can do it. Appreciate that.
Got it handled, my friend. Okay.
Thank you so very, very much, all our listeners, for taking the time to listen to this.
Thank you, my friend. That was wonderful.
Thanks.
Okay. Ciao. Bye.
So to summarize what Morten has said, he has taken the RF supercomputer and made it do HD radio, and that includes the functions of direct-to-channel exciter. He's taken and actually put the X-Gen functions that we described before into that same RF supercomputer. So the mathematical capability of the RF supercomputer is providing the functions of the X-Gen. And he's got advanced adaptive precorrection, which includes both linear and nonlinear samples and memory effect correction uniquely. It has GPS for timing and exact frequency lock. And another thing we haven't mentioned is this RF supercomputer is going to be able to bring in audio using the new ATSC3 STL protocol. And why that's important is that there are audio processing people who are producing audio processors that can send the audio in ATSC3 STL mode. And the advantage is that that includes all kinds of not only error correction, but also security, so that hackers can't come in and easily transmit on your frequency by hacking your STL stream. So really cool stuff coming down the road. This is going to be an exciting product. And I'm really glad we have this opportunity today to talk about it. You've seen it in action. You've seen the user interface there. It's still under development, but it does work. It does make HD radio, and watch this space. As Morten talked about, adaptive pre-correction. Maybe, Perry, you'd like to explain this slide.
Well, I think Morten actually did a pretty good job.
Yeah, tough to beat the doctor.
But what he was explaining was that we have, typically on a radio system, you typically have a nonlinear feedback sample that you then correct. And if you do actually have any filtering components out of bandpass filters and so forth, you take a sample after that, and that was able to actually correct for any phase or phase errors in the system. So the correction system that Morten has put together can do both linear and nonlinear at the same time, and this really does do a great job at improving the signal to noise. And as we know, signal to noise, the better the signal to noise, or the better the MER, as Morten mentions, gives us better coverage, gives us the ability to receive the signal in more, let's say, difficult places to receive signals, and generally makes the transmitter a lot more efficient as well. So we're looking at some significant benefits here.
The other thing that this slide points out, Perry, and I think we should mention, is the other HD radio equipment on the marketplace, including the part that has been developed by Broadcast Electronics over many years, has only a nonlinear sample. That is the part that is coming from the output of the PA and coming back and being corrected. The linear pre-correction, which we've included in our new advanced adaptive pre-correction, has not been a function in radio, FM, HD radio transmitters, and it can be valuable. This has been a technology that's been developed for television, and in television they use a channel filter, and that channel filter has both frequency response or amplitude distortions, but also phase distortions that can cause problems in the output. So what happens is you bring back a sample after the bandpass filter and pre-correct for that as well. So you have both linear and nonlinear correction. Now, as I said, if we just have a low-pass filter at the output of the transmitter, it's not really a big deal. It's a very broad-banded filter. However, many stations these days are using combiners, where they're using multiple transmitters going into a common antenna, and those bandpass filters in those combiners suffer from the same sorts of linearity issues, and this system can automatically correct for that. Mm-hmm. Pretty powerful.
Absolutely. Yes, it certainly is. I think it's great technology that Morten has taken mostly from the TV side and moved it into the digital radio side.
Absolutely. All right, let's see here. So we talked about what the advanced adaptive pre-correction, the nonlinear distortions, We talked about memory effects. Morten did a good job of explaining how the memory effects degrade the signal, and they really haven't been corrected for in previous implementations for HD radio. And so this memory effect correction is an advanced technology that improves the MER, or it can improve the efficiency of the amplifier. So what's coming up next for the Elenos group? We're committed to digital radio. We believe that digital radio is the future for radio. And the new RF supercomputer will be available in Q3 of 2020. We will be taking advanced orders soon. A new importer and exporter are also going to be released at the same time. And the integration of the importer and the exporter into the exciter will be released in 2021. All of those four things, or three things, are intended to do a couple of things. Number one, to reduce the purchase price for HD radio, make it available to a broader spectrum of people, and to simplify the whole process of going to HD radio. To be fair and honest, the very first HD radio implementations that were available in our industry were science projects, and they were complicated and difficult. And now, with this technology, we believe we're going to be able to make HD radio plug and play for people. A new range of FM products has been derived from our ETG and STX lines. Will also be available before the end of 2020, a new series of FM transmitters that all support digital mode operation and provide the highest efficiency in the market, as well as providing some unique features in redundancy and reliability. Watch this space. We also have some new products available you would have seen if you had come to the NAB show and we were able to be there. You would have seen the new STX3. I recommend you talk to your broadcast electronics sales representative for information. A new enterprise cloud version of the Audio Vault, a new series of Marty STLs, and a unique, wonderful, high-tech test and monitoring system for both AM and FM, actually, called the Avatar. And we've got webinars coming up in the future on all of these. And the same page, www.elenosgroup.com/webinars, you can sign up for all of those coming in the future. We believe HD radio is here to stay because there's 65 million receivers worldwide. It's the perfect time for a new HD radio exciter, importer, exporter product technology with new radio transmitter technology. Technology changes quickly. And one of the things that the RF supercomputer provides is it provides a platform that future-proofs your technology. We can make changes. We can go to all digital HD radio, and it's all in that board. We just changed the software load. The Elenos Group has 90 years of corporate experience, 60,000 installations worldwide, and some exciting new products for all radio stations. And you can register for our schedule of upcoming free webinars at elenosgroup.com/webinars. I don't think we've got a lot of time for questions, but let me see if I can get to some of them really quickly here. And there's a question from Daryl. Will this webinar be available at a later date to view again or show to a group? Absolutely. We should have that up by Monday. Some questions about the availability of this webinar in Spanish. Sorry, no habla español. But we'll do our best to have similar content available in the future. And Kent is suggesting that perhaps he didn't see much except for the block diagram for quite a while. So it's possible that not everybody was able to see the camera of Morten. I am sorry for that.